Hello, everyone. We're going to move on into chapter 4, where we'll continue talking about different types of isomers and orientations in space. We first introduced this concept when introducing the idea of a stereoisomer in chapter 3. So today we're going to talk about the concept of chirality and, in particular, how that can lead to something called an enantiomer. So remember that organic compounds can be described using different levels of structure. We've used a lot of these words so far. We've talked about their composition, which just means their molecular formula, their constitution, which is how many atoms or how the atoms are connected and the patterns of their bonding. The configuration, which is the three-dimensional positioning of the atoms, and the conformation, which is the position of groups with respect to bond rotations. So remember, we talked a lot about that during our chapter 3 discussion on Newman projections. And each of these levels is associated with a type of isomerism. For example, configurational isomers differ in configuration, but are identical at higher levels. So here you can see a configurational isomer would be an example like dimethylcyclopentane being in the cis conformation or the trans configuration. So what is chirality? A chiral molecule, a molecule that has chirality, is not identical to its mirror image. So you can see in this example here, a chiral molecule, when you make a mirror image of it, it is not superimposable on its mirror image in 3 dimensions. Now, a molecule that is superimposable on its mirror image, we call achiral. Chiral mirror images exhibit an interesting kind of configurational isomerism. So this is, again, a isomerism where we're looking at arrangement of the molecule in space. So here we see molecules A and B are mirror images, but they are not superimposable on another. So they are chiral. It's impossible to try to align all 5 atoms in A onto B. And actually, I think if you look at this section right here, we've taken A and B and their mirror images and then rotated B so that it's facing in the same direction as A. And you can see that there's a chlorine here instead of a bromine. And where this chlorine is, this bromine is. So they don't line up. Now, one of the classic examples of chirality and mirror images are your own hands. In fact, we will talk about rotation in handiness because this is such a classic example. So if you put your hands together with your palms together, you'll see that your hands are mirror images of each other. However, if you were to try to stack your hands on top of each other with the palm of one hand on the top of another hand, of course, they do not line up, right? Your thumbs or none of your fingers really match. So your hands are also chiral. So when you have something that is a mirror image of the other, but it is not superimposable, the molecule is called an enantiomer. So an enantiomerism relationship between 2 molecules is, as said, when they are chiral and they are non-superimposable mirror images. Now, a molecule can't be an enantiomer in isolation, right? Because if one exists, the other must as well. So you will always have a pair of enantiomers from a molecule. Now, I want to note something here because we're going to talk about it later, but one of the key signatures of chirality is that you have 4 different groups attached to a tetrahedral carbon. This is one of the signature things to look for to define chirality. 4 different groups attached to a tetrahedral carbon. This usually leads to a chiral molecule. And remember, many molecules are identical to their mirror image, but that doesn't mean that they're also not superimposable. You can always test by reflecting the molecule through a mirror in your mind and drawing it out, and then trying to superimpose the mirror image onto the original. So if we look here at this CHClF2 and take its mirror image, here's the original and its mirror image, you can see that these are in fact superimposable, right? We can line up all of these in a matching manner on top of each other, making them achiral. This is just the same molecule. We did not form an isomer.